So this video is going to look at the types of bonding found in the first 20 elements of the periodic table. Now the first 20 elements take us from hydrogen to calcium, and there's only 4 types of bonding found within these 20 elements. We have a metallic lattice or metallic bonding. We have the monoatomic elements shown in red. We have covalent molecules, and we have covalent networks. It's really important that you always remember there are no ionic elements. We only have ionic compounds. We do not have ionic elements. So we're going to look in more detail at these 4 groups, describing what the type of bonding is and how that influences the properties that those elements have. You should hopefully notice that carbon is coloured in both green and blue. That is because it exists in multiple forms, some of which are covalent molecules, some of which are covalent networks, and you do need to know the differences. So the first group we're going to look at are our metallic elements. So this is quite a big group. It's lithium, beryllium, sodium, magnesium, aluminium, potassium, and calcium. Unsurprisingly, metallic elements have metallic bonding, in which we have our positive metal ions surrounded by what we describe as a sea of delocalized electrons. And metallic bonding is the electrostatic force of attraction between positive metal ions and delocalized electrons. These delocalized electrons allow metals to conduct heat and to conduct electricity. Metallic elements also have quite a mixed range of melting points. So elements like mercury, for example, are liquid, whereas most metals are quite solid. However, one common trend we see for metals is that they always have very, very, very high boiling points. It is hard to turn a metal into a gas because metallic bonding doesn't really allow for itself to be broken up into gas. The next group are our monoatomic elements, and we only see these for our noble gases. And in the first 20 elements, the noble gases are helium, neon, and argon. Monoatomic just means single atoms, and we see that these monoatomic elements exist as single atoms on their own. They are all gases, and they have very, very, very low melting and boiling points. And they do not conduct electricity, because you need to be charged in order to conduct electricity, and they are not. Now, even though they exist as single atoms on their own, there are intermolecular forces between them. So we have things called London dispersion forces. Now, London dispersion forces are a type of intermolecular force, and it's just something that does hold the atoms together in a way that stops the gas from just spreading everywhere. There are some forces of attraction between the atoms. Now, we can see that there definitely has to be some sort of force between them, because when we go from helium to neon to argon to krypton and then to xenon, we see this big increase in boiling point. So there has to be something, some factor that causes these single atoms to have different boiling points, and it is the monoatomic elements getting bigger and having heavier or stronger forces. And this is because those London dispersion forces that exist get stronger the bigger the atom, or more specifically, the more electrons an atom or molecule has, the stronger the London dispersion forces are. So bigger atoms will have more electrons, which means they have stronger London dispersion forces, which you'll sometimes see shortened to LDFs. Please don't write LDF in an exam, write London dispersion force. And if you've got stronger forces, it means you'll need more energy to pull the atoms really far apart to make them a gas, and that's why we see this increase. So it shows that even though they are single atoms, there are still forces between the atoms, but they're quite weak, which is why they're all gases. Next, we're going to move on to our molecular elements, our covalent molecular elements. And these include hydrogen, carbon, nitrogen, oxygen, fluorine, phosphorus, sulfur, and chlorine. They all consist of discrete molecules of varying size. Now, discrete means that you can count the number of atoms in it, and each molecule, whenever you count the number of atoms, will have the exact same number. Now, covalent molecules have low melting and boiling points, and they have low densities. So even if they're solids, they do tend to float on water. They do not conduct electricity. And as I said, the fact that they're molecules means that you can write an exact formula with an exact number of atoms in it for each of these. And we can divide the covalent molecules into two groups. We have our diatomic elements, and we have our slightly larger molecules. So our diatomic elements we'll look at first. In these ones, we're looking at hydrogen, oxygen, nitrogen, and then our halogens, which is group 7. So in the first 20 elements, that's only fluorine and chlorine. However, diatomic elements extends all the way down through bromine, iodine, and acetylene as well. Now, diatomic, monoatomic meant one atom, diatomic means two atoms. And these two atoms have a covalent bond between them, which means they're sharing electrons. And because they are the same atom, which means they're going to have the exact same electronegativity, the electrons are going to be shared equally between the two atoms. The covalent bond between the atoms is strong, but between different molecules, we only have those weak London dispersion forces as we saw for our monoatomic elements. This is what gives them low melting and boiling points. So for example, here we have got fluorine. Now each fluorine molecule has two fluorine atoms in it, and they're held together with a really strong covalent bond shown in blue. However, those two molecules still have a force of attraction between the two of them, but it's a weak intermolecular, so between molecules force, and it's a London dispersion force. Moving on to our larger covalent molecules. In this case, we're really only going to be looking at phosphorus, at sulfur, and at some versions of carbon. So phosphorus as a molecule exists as 4 phosphorus atoms in a tetrahedron shape. And as you can see, there are some forces between the two molecules. Sulfur exists as a sulfur 8 molecule. It's sometimes described as a crown shape, which I don't know why it doesn't really look like a crown, but S8. And you can see its melting point is larger than that of phosphorus. The bigger the molecule, the bigger the melting point for these molecules, because larger London dispersion forces. And finally, we have carbon. And there's 2 forms of carbon that exist as molecules. We have fullerenes, which are sort of ball-shaped, and they can have 60 carbons, 70 carbons, and even up to 240 carbons in them. That's one molecular version. There's also carbon nanotubes, which are cylinders, and they tend to have very, very, very large numbers of atoms, but they are still molecules. Now with these, all 3 of those elements are solids, which is unusual for covalent molecules, as we usually associate them with being gases or liquids. And they still only have London dispersion forces between the molecules. But remember, London dispersion forces were affected by the size of a molecule or the number of electrons it has. In these molecules, because they are a lot bigger than diatomic elements, it means their London dispersion forces are a lot stronger, which means that the London dispersion forces actually allow them to exist as solids, but they will still have low melting and boiling points and can easily be turned into liquids. The final thing we're going to look at are our covalent networks, and these include boron, carbon, and silicon. From National 5, you're aware of carbon, but boron and silicon are also involved. Luckily at Higher, all you need to know for boron and silicon is that they exist as covalent networks. you don't need to go into detail about what the networks look like, but for carbon, it's exactly the same as for National 5. We need to know the two different forms of carbon. Now, a network, all that means is that you've got millions of atoms held together with millions of strong covalent bonds. So if you're trying to melt this, you're having to break covalent bonds. Each network can be of a different size, which is what makes them different from molecules. You cannot write an exact formula for diamond because every diamond is a different size. Whereas you can write a formula for something like phosphorus, P4, because every molecule has 4 phosphorus atoms in it. Carbon can exist in 2 network forms, as well as the molecule forms that we just looked at the previous slide. And you need to remember which 2 are molecules and which 2 are networks. The 2 networks are, firstly, diamond. And this is where each carbon is bonded to 4 other carbons, creating a tetrahedral pattern. It cannot conduct electricity, and it's one of the hardest substances known to man. The second version is graphite, which is what you'll find in a pencil lead. It instead has 3 bonds forming between carbon atoms, and it forms in layers. And actually between the layers, we have London dispersion forces, which means that the 2 layers, sorry, not the 2 layers, but all the layers, are not held very strongly together. Graphite is unusual because it can conduct electricity even though it is covalent. This is because each carbon is only forming 3 bonds and has a leftover electron, which becomes delocalized. And finally, because the layers are held together by London dispersion forces, which means it can easily be broken away, it means that graphite can be used as a lubricant for machinery, so a solid lubricant rather than a liquid. And also the reason why it's useful in pencils is because every time that you make an interaction between pencil and paper, you're breaking off layers and leaving layers of graphite behind from the pencil. That's what's happening. So finally, to summarize, we'll just look at this version of the periodic table again. Remember, we have our metallic elements, we have our monoatomic elements, we have our covalent molecular elements, and we have our covalent networks. There are no ionic elements. And the final thing to remember is just be careful with carbon. Carbon has fullerenes and nanotubes, which are its molecular forms, and it has diamond and graphite that are its network forms. Okay, thanks for listening to the video. Hopefully you'll now be able to answer questions on the bonding that exists in the first 20 elements.